average CLT for tau k, so for the reaching time of site k. And okay, if we have some time, I may say something about how to convert this in a result for the random walk itself. Okay, so what's the result? Well, recall that we have defined sigma 1 as the square root of the expected quenched variance of tau 1. Okay, and I've given an expression even for it as an exercise, and as far as I could check, this expression was correct. So this is equal to this. Yes. Yes, okay. And now I'm going to define sigma 2 square. Okay, and for sigma 2 square, okay, let me put some dots here because I'm going to need some notions. So, okay, I mean, here I could put j plus 1, but you have translation points. Okay, and what is sigma 2 square? Well, it's the sum over j in z of the expectation of v0, vj. Okay, and I'm going to prove later that this sum, I mean, that this thing is summable and that the sum is finite. But let's accept this for the moment. And finally, we define sigma square, which is sigma 1 square plus sigma 2 square. Okay, so in particular here it's worth sigma square. It's not, and it's strictly larger than the variance under E0 of tau 1. Okay, which is what you would find in the central limit theorem for IID random variables. And the idea is that, well, it's simply the variables are correlated. It's not too difficult to see that they are positively correlated, in fact, so this will have an effect in the variance. Okay, so what is the theorem? What are we going to prove today? Well, we are going to prove things in 2 steps. So first thing is that we are going to prove a central limit theorem, well, for the sum of the VJs, okay, and then we are going to prove a central limit theorem for really for tau k. Okay, so what's the theorem? Well, first thing is A, so under P we have that the limit when k goes to infinity of E0 omega tau k minus E0 tau k divided by square root of k. Well, this is equal in distribution to Z2, where Z2 is a normal variable with variance sigma 2. Okay, this thing here, I mean, it's also the sum from k equal 1 from j equal 0 to k minus 1 of vj over square root of k. Yes, okay, yes. Okay, I mean, to get this expression from that one is just well, you iterate the strong Markov property, okay, to decompose this into a subgroup. Okay, to reach tau k, you first need to reach k, you first need to reach 1, then 2, then 3, and these vj's are just the expectation of the increments. Okay. So this is the first result, and this is what's going to take us much time. The second result is that under E0, we have that the limit when k goes to infinity of tau k minus E0 tau k divided by square root of k is equal to z in distribution, when this is converged in distribution to a normal variable of variance sigma square. Okay, is it clear what the results are? Okay, and the first thing we are going to do is to prove B, assuming that A holds. Okay, and of course using the quench central limit theorem that we have proved last time. So proof of B assuming A. Okay, so I'm going to define, well, yk1, which is tau k minus E0 omega tau k divided by square root of k. Yk2, which is E0 omega tau k minus E0 tau k over square root of k. And yk is simply equal to yk1 plus yk2. Okay, and yk is, well, it's exactly this, right? Unless I've made a very silly mistake in writing things. Okay. So we want to prove a CLT for yk. I mean, the idea is that basically these two things are independent Gaussians, but well, it's only true asymptotically, right? I mean, the idea is, I mean, like yk is clearly something that depends on omega, so it's not really independent of that. But the idea is that asymptotically you don't see this dependence in the distribution, and this is what makes things work. So I think the cleanest way to see this is using Fourier transform. So, okay, what we are looking at is this exponential I psi yk. Okay, we want to prove the convergence of this thing. Okay. And what we can do is, well, we can rewrite this as a double expectation. I mean, first with respect to the environment, then with respect to the quench distribution. And yeah, yk, did I do some, yeah, no, so yk 2 does not depend actually on the quench distribution. It only depends on the environment. So this is equal to this. Okay? Okay, so now we know that this thing converges. Okay, because we know already that we have a quench central limit theorem. So we know that this thing converges P almost surely. Okay, so what we can do, we can just replace this by its limit. So this is equal to exponential minus psi square sigma 1 square over 2. Plus well, the expectation of this and then I guess I can put this there. Minus exponential minus xi square sigma 1 square over 2. All good? We have two terms. Okay, I've just added this and subtracted it. Okay, nothing more. So now we have 1 and 2. So the limit when k goes to infinity of 1, it's equal to exactly what we want. So and here we are using a, I guess. This is equal to exponential minus xi square sigma 1 square plus sigma 2 square over 2. And now if you look at 2, well, you see that the integrand, let's see. Yeah, okay. Well, it's smaller than 2, okay. It's, I think most likely, yeah, okay, it's smaller than 2. And by the quenched central limit theorem, it converges to 0. To 0, P almost surely. So using this consideration, we can use dominated convergence, and this is equal to 0. So far, so good? Okay. So, yeah, so now we need to prove A. And, okay, so this sequence Vj here, it's an ergodic sequence. And there is a central limit theorem available for ergodic sequences according. Well, but the thing is that yeah, its proof requires a few steps, and I wouldn't want to go through them. So instead of giving you a black box result, I want to give you a complete proof using a very well, basically by bare hands. And this method is actually quite useful when you need to prove a CLT and it doesn't fit any nice setup in which CLTs have been proved. Okay, so basically what you want to do is, okay, so this method is called method of moments. And well, it's based on a theorem that I'm going to write now, which says that, well, if you want to prove that a random variable converges, a sequence of variables converges in distribution, well, you just need to show that all the moments converge, provided that the moments characterize the limiting distribution. Okay, and Yeah, I'm going to prove a slightly weaker version of the result, just for convenience. But the full version is not much more complicated to prove. But okay, in practice, somehow, let me write the result and then we can discuss it. Okay, so theorem. Let zk be a sequence of real valued random variable that satisfies limit when k goes to infinity of the expectation of zk n equals mu n. And assume that there exists z such that expectation of z to the power n is equal to mu n for all n. And two, that for all psi in R, the sum of psi n to the n mu n from n larger than 0 is finite. Okay, then zk tends when k goes to infinity to z. Okay, then you have convergence in distribution. Okay, perhaps, I mean, if you want to write things correctly, you need to say there exists a sequence mu n such that. Okay, so yeah, the result. Okay, I don't want to go into too much technical details. Somehow, 1 is implied by 2. Okay, you don't have this is not necessary. This is not an extra assumption, and 2 is not really necessary. You just need to say that this variable here is unique. Okay, that there is only one distribution that satisfies this. This is clearly a sufficient condition for z to be unique, just using Fourier transform. Like this characterizes the Fourier transform. But yeah, it's not. I don't know exactly what the optimal condition is, but at least if you have this for psi sufficiently small, for instance, this is also sufficient. Okay, so and of course we are going to want to use that to prove a Gaussian central limit theorem. So for Gaussians. Mu n, okay, mu 2n plus 1 is equal to 0, and mu 2n is equal to 2n factorial divided by 2 to the power n factorial, and sigma to the 2n. So, well, of course, in case of Gaussians, this is true. Okay. So let me give you a proof of this. You can tell me if you don't need a proof, but I guess this is new at least to some of you, right? Okay. Okay, so what we are going to try is to, well, we want to estimate the limb soup, okay, of this thing. I'm just assuming that I'm constructing zk and z on the same space. Well, because I'm not using the joint distribution here, I do not need to say anything. I mean, you can assume just that they are independent if you want. Okay. So I want to say that this is equal to 0. Okay, so what I can do is decompose this in 2 pieces. So what I will do is I will, well, take the Taylor expansion up to order, say, 2m minus 1. So this is, okay. So, and I'm going to use triangle inequality directly on the Taylor expansion. Okay. So, sum from k equal 0 to 2m minus 1. And here I get, no, this is not k, this is n. Here I get I psi zk to the n divided by n factorial. Minus I psi z to the n divided by n factorial. Okay, and then I get a rest term. So okay, where here are psi u. Okay, this here is zk, and here I should put some n as well. Okay, but m. But what's really important is that, okay, so this is just, well, exponential minus some m equals 0 to 2n minus 1. Yeah, okay. IU, let's write it. IU to the m divided by m factorial. This is better like this. This is Rm u. Okay, and what I want to use is that Rmu is smaller than 1 over 2n factorial u to the power 2m. Okay, this is true just because, well, if you take the, well, if you take any derivative of this function, it has always modulus 1. So when you bound the Taylor rest, well, you have, yeah, the supremum norm of the derivative of order 2m, but you can ignore this, and then you just have this. Okay, so here you have finitely many terms. Okay, This is 1 and this is 2. So the limit when k goes to infinity of 1 is equal to 0. This is just my assumption. Okay, I mean this is just mu n, and this converges to mu n. Okay, and there is a factor in front that you don't care. And this is a finite sum. Okay, so for any m, the limit of 1 goes to 0. Now, what you have is that, well, 2, well, it's smaller than 2 psi to the 2m over 2m factorial. No. There is no 2 here, and here you have e to the zk 2m plus e to the z 2m. Okay, so basically you have that lim soup of 2. When k goes to infinity, well, it's smaller than 2 psi to the 2m, 2m, and mu 2m. Okay, this is equal mu 2m. This converges to mu 2m. And we are good. Okay, so therefore the lim sup of what we want, I mean, it's smaller than the sum of the lim sups, so it's smaller than this. This is true for arbitrary m. And this thing here, it's summable. So in particular, it converges to 0 when m go to infinity. Okay, and here, well, okay, I can put an absolute value here, but okay, perhaps it's better. You just have to put this here. Okay, so now we are left with proving convergence of moments for, well, our sum of VJs, if you remember what the VJs are. Okay, so some people, some of you might already foresee some problem, but we are going to get into that. Okay, so yeah, let's remember what the VJs are. So VJ is equal to the sum, no, not the sum, it's equal to the expectation j omega to j plus 1. Okay, and minus, I recenter it, E0 to 1. Okay, I'm going to rewrite this, okay, because this is going to be convenient. So another way to rewrite this, well, is to use the explicit expression we have here. Okay, so the explicit expression is 2 plus something. But 2 is going to be recentered, so I'm just not going to write it. So we have the sum from k equals 0 to j. And I think then you have rho j rho j minus k. Okay, and then you have to recenter it. So here I'm going to subtract e rho 0. And I think I have to put it to the power k plus 1. Okay, so just for the computation, I'm going to write this as alpha. Okay, so alpha is going to be e to the rho 0, and beta is going to be e to the rho 0, 2. And by assumption, and I forgot to write the assumptions in the theorem, but both of them are smaller than 1. Okay, because we have seen that this is a requirement to have a central limit theorem somehow. Okay. Okay, and yes, the first thing we want to prove, okay, is the convergence of the second moment to sigma square. Okay, so limit. Okay, and now let me use the variable n. I think this will be more convenient because k is used here. So sum from j equal 0 to n minus 1 of j square divided by n. This is equal to sigma 2 square. And this is finite. Okay, so there are two things to prove, basically. This thing and this thing. Okay, so let's start with this, and we are going to prove this afterwards. Okay. Okay, and yeah, here I should put a sigma 2 because this is, we want to prove that. Okay, so yeah, things could be computed exactly, but I'm going to prove upper bounds because this is going to be easier. Okay, so let me compute the covariance between V0 and Vj. So what can I do here? Well, yeah, what we have already proved, okay, is that yeah, we have already proved that this is finite because we know that the expectation of V0 squared is finite. Okay? So, because we have proved that we have proved this, okay? If beta is smaller than 1. Okay, so there is no problem about the finiteness. So what we are going to show is that this decreases exponentially in J, so that this is summable. Okay, so let's assume, okay, so okay, by shift, okay, these two things are equal, so we can assume that J is larger than 0. Okay, and we are going to show that this decreases exponentially in J. Okay, so let's just here expand the sum. Okay, so what we have is that this is the sum from k equal 0 to infinity. Sorry, this is not there. Sum from k prime equals 0 to infinity. Then you have rho 0, rho minus k minus alpha k plus 1, and rho 0, rho minus k, rho j minus k minus alpha to k plus 1. Okay, so several remarks. Okay, so first thing is that, yeah, all these terms here, they are always positively correlated. Okay, but you can compute them exactly, but basically, yeah, if you have some rows in common there, you will get, well, some alphas for the rows that are not in common and some betas for the rows that are in common, and beta is larger than square root of alpha. So this is going, what you're going to have is going to do more than compensate this. Okay, so yeah, so let's put this inside, okay? And let's look at each term. Okay, so what you can say is that okay, and the covariance term, yeah, I shouldn't have written it like this. You can rewrite the covariance term as E k prime, rho 0, rho minus k, rho j, rho j minus k prime, minus alpha k plus k prime plus 2. Okay, I mean the covariance is just it's just the expectation of the product minus the product of the expectations. It's just the other way to write it, and in our case it's more convenient. So this thing, it's equal to 0 if k is smaller, if k prime is strictly smaller than j. Okay, if k prime is strictly smaller than j, then this thing is larger than 1, so you don't have terms in common. And it's smaller. So a way to bound things is to say, well, all the terms are in common. Okay, basically, if a term is in common, you get square root of beta for it. Okay, you get beta, but beta is for 2 terms. And if it's not in common, then you get alpha. But alpha is smaller than square root of beta. So you can just say, okay, I mean, so when you can just ignore this thing, and this thing you're going to bound it by beta to the k plus k prime over 2 plus 1. Okay? So this gives us a bound. You get that this is smaller than the sum from k equals 0 to infinity, the sum from k prime larger than j, larger or equal to j, Okay, here we are using that j is larger, is positive. And then you get beta to the k plus k prime over 2 plus 1. And yeah, so you just want to show that things are finite and decrease exponentially in j. I think this sum is exactly equal to beta over 1 minus square root of beta to the j. No, 1 minus square root of beta and square root of beta, well, beta to the j over 2. Okay, I mean, you just shift the indices here. You get this beta over j over 2 that goes out, and then you have two geometric sums. So this gives you, yeah, you have a square. Okay, not really important. I mean, it's not meant to be optimal. The important thing is that this decreases exponentially. Okay, so my thing is sum. Okay, so, okay, we have done the second moment. The first moment is for free. So I don't know, perhaps we can do the third moment. And perhaps someone can tell me the problem, the kind of problem I run into when I try to compute the third moment. Okay, so remember that my assumption is just that beta is smaller than 1. I have no other assumption than that. Okay, and uniform ellipticity. I'm going to keep uniform ellipticity because this is going to help. But yeah, uniform ellipticity, I'm going to use it, but it's easy to see how you can play around this in the proof. Okay, but what's going to give me trouble here? Well, if E rho 0, 3 is larger than 1, then E of V0 to the 3 is equal to infinity. So, okay, so this was a nice try. No, okay, we're going to do something else. Yeah, so the idea is to try to go back to what, well, yeah, so for the method of moments to work, well, okay, you need your variables to have all moments. And there is something that is going to be helpful. Like if you try to use, basically, yeah, you can try as an exercise to use the moment method to prove the central limit theorem in the case of bounded IID random variables. Okay. Yeah, I have not explored a lot the literature, but apparently this is what Chebyshev did originally to prove the central limit theorem. Yeah, independence helps you a lot to deal with this sum when you do this expansion. So, okay, here our variables are dependent, but what we can try to do is to make the dependence finite range. Okay? So, what can we do to make the dependence finite range? Well, we can just cut this sum here. Okay? Instead of summing up to infinity, we are going to cut this sum somewhere. Perhaps it's not completely obvious where you should cut it. Basically, you can cut it anywhere as soon as where you cut tends to infinity. Okay, so I'm going to cut it at a level that depends on n. Okay, where n is the number of v's that I'm summing. Okay, and then I want several things. Basically, when I'm computing the moments, I'm going to deal with powers of n. So anything that is small with respect to powers of n is not going to be a nuisance. Therefore, yeah, if I want to make this thing here always smaller than the power of n, what I should do because each of these terms are bounded, is to make the level at which I cut strictly smaller than log n. Okay? Because then I have this to the power k0, okay, where k0 is a Mach thing. This will be n to the little o of 1. Okay, so this is the rationale behind this choice. So k0 is equal to square root of log n, okay? And Vj is equal to the sum from k equal, okay, Vj bar is equal to the sum from k equals 0 to infinity of rho j minus sorry. Rho j minus k minus alpha to the power k plus 1. Yeah, I can put k0 minus 1. Okay. And perhaps, yeah, okay. So this is what we are going to do. Okay, let's keep that there, and let's prove B, because we haven't proved B. Okay, and then we are going to take a break. But then what we really want to prove perhaps is, okay, let's prove B, and then basically you want a B prime that would be valid for this, and you want to show that the rest really has small variance, but this will be included in that proof. Okay, so yes. The expectation of the sum from j equal 0 to n minus 1 of Vj. Okay, what is this minus n sigma 2 square? Okay, we want to show that this thing is little o of n, basically. So this thing, okay, so this thing is the sum from j equal 0 to n minus 1, the sum from L equals 0 to n minus 1, times the expectation of Vj Vl. Okay, and the second term, well, I can rewrite sigma 2. So sigma 2 is sorry?
Is there a square missing?
Yeah, of course there is a square missing. Yeah. Okay. So what's n sigma 2? So n is just, well, the sum from j equals 0 to n minus 1 of 1. Okay, and sigma 2, well, it's a sum from L on L in Z of E V0 VL. Okay, but this is the same, right? Just by translation invariant. Okay, so basically I have the same things here and there. Okay, so perhaps I should put a plus here and a minus there. Okay, just for convenience. Because here I have more terms. Okay, so I just have to show that the sum of these extra terms is small. Okay, so what I get is the sum from j equal 0 to n minus 1, and the sum from L not in 0 n minus 1 Vj Vl. Okay, and well, here it's not complicated that by symmetry somehow the contribution of L smaller than 0 and n larger than n minus 1 is going to be the same. Okay? Just because this is a function of L minus j. Okay. Yeah, okay, I mean, we can even ignore this. This thing here, it's smaller than, okay, beta over 1 minus square root of beta square. And here you have beta to the power L minus j over 2. Okay, and then you can check that this is summable. Okay, this sum here, it's finite. Okay? I mean, on one side, basically, you're summing on L smaller than 0 and j larger than 0. Okay? So you just have a double geometric sum. And on the other side, you're summing on L larger than n and j smaller than n. So you just have double geometric sum. Okay? So this sum is bounded by something which is also explicit. I mean, it's probably something like, I don't know, beta 2 over 1 minus square root of beta to the 4. But, and perhaps there is a 2 because you have two sums. I don't know, something like that. Okay, so you need little o of n, so this is more than what you wanted. Okay, so now, yeah, maybe I can add C and D to the lemma. So what's C and what's D? Well, the limit when n goes to infinity of the expectation of the sum from j equals 0 to n minus 1 Vj bar square over n is equal to sigma 2 square, and the limit when n goes to infinity of the sum from j equal 0 to n minus 1 of Vj minus Vj bar square divided by n is equal to 0. Okay, so why is this true? Well, okay, all things you are summing here, they are all positively correlated. I mean, like, you have a sum of sums, okay? But all these terms here are positively correlated. So what you have here compared to before is that you have less terms. Okay? But what you can check is that all the terms that really contribute to the sum, they are still there. Okay? Because the terms that comes from the large case, they don't count. Okay, so this is the reason why this is true. And here what you get is a strict subset of the terms that you have not counted there. So this is the reason why. Okay, and perhaps a last remark, just to justify that you can proving central limit theorem for this sum is sufficient. Okay, so I don't know. Maybe I should give a name to this. This thing is going to be V star J. Okay, I'm just going to use once. Okay, so you have the sum of the Vj's from j is equal 0 to n minus 1 over square root of n. It's equal to sum j equals 0 to n minus 1. Okay, so yeah. Using D, this thing converge in distribution to 0 when n goes to infinity. Okay, and so now if this converges to a Gaussian and this converges to 0, well, okay, if you have something that converges in distribution, if you add to something, if you add to it something that converges to 0 in distribution, then the sum converges in distribution to the same thing. Okay, you have to be careful with this kind of statements. If you don't believe it, you just prove it again, but it's not, okay, it's reasonable and it's not hard to prove. Okay, so we are going to prove CLT for that, and for this, like these variables now, they are now, I mean, compared to Vj, the advantage is that they are bounded. Okay, they are bounded by something that depends on n, but they are bounded. Okay, just because my rows, they are bounded, yes, they are bounded. Just because my omegas, they are bounded away from 1 and 0. Yeah, they are independent at finite range. Like if J and L, if J and L are distant of more than K0, yeah, if J and L are distant at least K0, then V bar J and V bar L are independent. Just because all the rows that appear in this sum, they concern different sites. Okay, so this is what we are going to use. Let's take a small break here. this converges to a Gaussian. So this is somehow the first thing you want to prove for the method of moments. And D, you want to use it to say, well, proving the CLT for V bar is the same as proving the CLT for V. Okay, so yeah, yeah, so this is for CLT for V bar J, and this is this implies that okay, if you want sum of Vj over square root of n will equal sum of V bar j over square root of n plus little o of square root of n. Okay. Okay. Yeah. Another question showed up during the intermission. Why is Vj equal to this? So the answer to this question is no. So it's not equal. So what is it equal to? Okay. So yeah, I think I can erase this. And yeah, so E j omega to j plus 1. Okay, well, it's equal to 1 plus 2 sum from j from k equals 0 to infinity rho j minus k. Okay, and this is not the first expression you had. The first expression you had was this one, but it's easy to see that the two are equivalent. So this is, and you get the sum. I think from k equal 1 to infinity of 1 over omega j minus k rho 0 rho j minus k plus 1. And do you sum from 0 or from 1? You sum from 1 because this is the term 0. And this is rho j. Sorry. Okay. So these two things are equal. It's just well, it's just you rewrite 1 over omega j as 1 plus rho j. And, okay. So now why is this true? Well, well, you're just recentering each term here separately. So this one disappears, and the others, well, you just have to subtract the expectation. And yeah, this is the time where I should ask, are there any other questions? Okay, so let's move to the proof of the moment. So we've proved that the second moment goes to the right thing. So let's try to compute the third moment. And I think this is somehow, like if you understand this, you understand the whole proof. So. Okay, so let me write it as a lemma. Yeah, I will write it like this. So it's the expectation of the sum of the Vj's from J's equal. Yeah, we are not going to use. We are not going to use complex Fourier transform for a while. So let's use this letter. I equals 0 to n minus 1 to the 3. Okay, this is equal to n1 plus little o of 1. Okay, so this is in particular little o of n to the 3/2, which is what we want to prove. Okay, so why is it true? Well, this thing it's equal to, the sum over I, J, L from 1 to n minus 1, E, sorry, and I forgot to put the bar, VI, VJ, VL. Okay, so now the important thing is that yes, so what you know is that Vj, okay, is independent of, first it's independent of omega x, x in z minus, all the coordinates that are involved in the definition of Vj, meaning it's basically j minus k0 plus 1, j. Okay, so because of that, if one of the indices here is at a distance more than k0 from all the others, then it's independent and you can factorize the expectation. And so if, say, I minus L is larger than k0, and I minus j is larger than k0, then the Vi, Vj, Vk is equal to E Vi, Vj, Vk is equal to 0. Okay, so all the terms that you have in the sum, they are just the terms for which all the indices are grouped together. Okay? Okay, because by symmetry, this is also true. Okay, so you can put here like an indicator, then j minus I is smaller than 2k0, and L minus I is smaller than 2k0. Okay, because if every index has somebody close to at the distance k0 from it, then they have to all be grouped together within distance 2k0. Okay, so and now we are done because this is smaller. Okay, what's the number of terms you have here? Well, it's n times k0 square, and then you have a constant in front. This is just a number of terms you have. Because this is the number of ways you have to choose I, and then you have 4k0. Yeah, I think you even have this here. But OK, that doesn't really matter. And then you say, OK, what's the bound for this? Well, OK, this thing, I mean, remember that omega is smaller than 1 minus delta. So rho is smaller is it what I want to say? I think what I want is it's 1 minus omega over omega. So omega is larger than delta. So rho is larger than, OK, 1 over delta. Smaller than 1 over delta. OK, I mean, rho is bounded by a constant. So I mean, you can just ignore this if you want to have a bound on V bar J. So here you have a sum until k0. This is dominated by a geometric sum of ratio 1 over delta. So yeah, you just change the value of the constant here. And you get 1 over delta to the k0. OK, this is exponential to the square root of log n. So this doesn't play a role. OK, so this is smaller than c and exponential c square root of log n, which is exactly what you wanted. Okay, so now this is okay. So there is something else to understand in the case of even moments, but for the case of odd moments, if you understand this, you have understood everything. But let's. The problem is just now it's not really yours; it's mine. I have to find a way to summarize this without the notation being a big mess. Okay, so what can you say about this? N to the, OK, so here I have 2n, and here I have m plus little o of 1, which is equal to O of n to the 2m plus 1 over 2. Okay, so how do you prove this? Well, we are going to do exactly the same thing. We are only going to keep non-zero terms, okay? And the non-zero terms, we are going to bound them by 1 over delta times, a constant times 1 over delta times k0 times 2m plus 1. Okay, so this factor won't be a problem, so we have to show, okay, so our expectation is equal to the sum over I1, I2m plus 1 of expectation V, I1, V, I2m plus 1. And we need to show that the number of non-zero term is, well, okay, yeah, big O of n to the n plus little o over 1. Yes. Okay, so so I think now this is okay. It's not really super necessary here, but it's a very important idea in statistical mechanics. Very often you have to deal with large sums, and they are difficult to control. And you can get things that are much worse than this. Yeah, when you cannot do computation, what you can do is pictures. This is the idea. So just going to try to replace this, to control this using geometric ideas. Okay, so yeah, you just consider a graph on 2m plus 1 vertices, okay, labeled by, this set. Okay, and my graph is actually something that will be dependent on the values of the i's. Okay, so the edge AB is present if and only if IA minus IB, well, is smaller than K0 minus 1. Okay. So now, if the graph has, well, okay, singletons. Okay, so singletons in the sense, if it has vertices that are not linked to any other vertices, then E vi1 vi 2m plus 1 is equal to 0. Well, just because you have one variable here which is independent of all the rest, so you can factorize. Okay, so basically you just need to look at this, okay, and try to find out, yeah, the number of i's that give rise, whatever, to a graph that has no singletons. Okay, so basically you can rewrite this sum as the sum over all possible graphs, and then the sum over all i's that are compatible with this graph. Okay, and m is fixed, so the number of possible graphs is finite. Okay, so this is just going to give you a combinatorial factor. So you just need to show that the contribution of each graph is smaller than n to the m. Okay, so let's take a good graph. Okay, and let's look at its number of clusters. So it has at most m clusters. Okay, by clusters I mean connected component, or maximal connected component, if you want. Okay, it's simply because if it's a good graph, then it has no singletons, so all the clusters have cardinality at least 2. So, and then we are done basically because you can overcount here. So let's say that, okay, let's say for simplification that okay, so yeah, I'm just losing a combinatorial factor. I'm just saying that clusters are formed with consecutive indices. Well, this is not really important. Then, okay, what I really want to do is basically, here you can overcount. Okay, you are going to factorize the sum and sum each cluster separately. And basically, the fact that this thing forms this graph, it gives you a constraint between indices in different clusters, and you can ignore it. You're just going to sum again. So what you're going to have is that, okay. The sum over IA, A in a cluster. Okay, so let's C be a cluster. Of E of the indicator that for all UV in C IU minus IV is smaller than K0. Okay, so this is really the number of index choice you have. Well, this is smaller than C times K0 to the C minus 1 times N. Okay, one index is free, and for the others you have at most, well, over the K0 choice. Okay, the constant here might depend on that. Depends on C. Okay, and then when you sum over everything, basically, you get just a product of this, but yeah, this M, you get it to the power of the number of clusters, so you get it to the power M. Is this good enough as a proof? Okay. I mean, in order to get things straight, you can just, look at how things work when things are independent. Okay, in that case, the terms that don't disappear are the terms where you have no single, where every index has to be repeated. Okay, and saying indices have to be at distance at most K0, I mean, this just yields an extra power of K0. Okay, so this is all good. Now we need to finally deal with, well, something which is more complicated in principle, because you will get a non-zero thing here, so you cannot neglect all the terms. Okay, an upper bound won't be sufficient. So let's prove the last thing, which is okay, what I'm going to show is this. So it's 2n factorial, 2n, n factorial, and here I will just put e to the sum from I equals 0 to n minus 1 vi 2. Okay, and plus something smaller. I think there's something smaller. Okay, we will see how small this is. Plus something smaller. Plus little o of n to the m. This first term, yeah, so everything here is m. I just copied this without thinking. Okay. So, yeah, so let's think about why this happens, and this also tells you why central limit theorem occurs. Okay, so one feature of central limit theorem is that basically the limiting law you obtain, it only depends on the variance, not on higher order moments. Okay, which means that, okay, the method of moments tells you that this has to be true when you have central limit theorem. And if you don't want things to depend on something else than the variance, then in your expansion, you don't want any third moment of any kind to appear. Okay, and here by third moment, I mean also like product of 3 dependent variables. Okay, so this means that the graphs that are going to contribute mainly to the sum, okay, are going to be the graphs that are perfect matching. Okay, so let's continue to elaborate on this. If, okay, all vertices have exactly one neighbor, okay, what's the number of perfect matchings? The number of perfect matchings is, well, okay, of course, it's factorial to m divided by 2 to the power m divided by factorial m. It has to be the case. Well, okay. You have to pair 1 with something, so you have 2m minus 1 choices. Okay? Then you have to pair, well, 2 with something, but 2 might be paired with 1. So you have to pair the next unpaired site with something. Okay, and for this you have 2m minus 3 choices. Okay, and here, okay, everything is labeled because in our sums we count things with labeled. Okay. And then you have, well, okay. 3 and 1. Okay, and this is exactly the term we have here. Okay. So, and well, if a graph is not a perfect matching and has no singletons, then it has at most m minus 1 clusters. Okay? It has a cluster of size larger than 3. It has no clusters of size 1. Okay, so this sum, okay, we can rewrite it as the sum over I1, I2m, E, indicator that the graph is a perfect matching. GI, okay. And, well, the same thing. Indicator GI is not a perfect matching. And has no singletons. Well, why? Because if it has a singleton, then in the expansion, this thing would be 0. And this second term here, okay, we know that, well, it's big O of n to the m minus 1 plus epsilon. M minus 1 is just a number of clusters. And you know that each cluster basically contributes to a factor n times some powers of k0 in terms of number of indices. Okay, now if this thing is a perfect matching, well, okay, you might just assume that, okay, and this is where, so let me call this 1. Well, all the indices, they have symmetric roles, right? So this is, so 1 is equal to, well, this factor, this factor here, this thing here, and here you have the sum over I, such that GI is equal to, well, okay. Yeah, okay, just, okay, GI, okay. I just identify a graph with a set of edges. Okay, this thing is equal to 1, 2, 3, 4. 2n minus 1, 2n. Okay, and then you get e to the vi1, vi2, e v I 2m minus 1 vi 2m. Okay, so like the final step is really to compare this to this. Okay? Okay, so what is this thing? Well, this is the sum over I1, I2, I2m minus 1, I2m of the same thing. Okay, so this thing, well, you don't have this indicator here, okay? This is from 0 to n minus 1. Okay, so somehow you have hidden somewhere an indicator. You have an indicator that GI contain all these edges, because if not, some of these terms would be equal to 0. Okay, because okay, so you just need to show, okay, this is larger than this. You just need to show that the difference is little o of n to the m. Okay. And again, we can just focus on the number of terms, because all the terms, like, they are bounded by yeah, just a constant to the power m. So. Okay, so yeah, so what's yeah, so that's it. Like now, if GI contains but is and GI not equal to the same thing, then GI has less than n-1 clusters. Okay, and we have already counted the number of indices configuration that yields less than n-1 clusters. This is of order n to the n-1. Yes. Okay, any question concerning the proof? Okay, and this kind of graphic reasoning, I mean, I don't know, there are some patterns that might be repeated, so basically, by seeing some of them, you might get better at this game. But when you have to prove something new, you might have to come with new ideas. But okay. And yeah, so maybe what I can do just to finish is, well, first ask for questions. No, and the next thing I can do is, yeah, to state finally the central limit theorem for xn, and to explain roughly, yeah, how it's going to be proved, and then we are going to do this next week. Okay, you have a quench version of this result. Let's focus on the average one. The proof is the same in both cases. It's just that in the quench case, the centering has a bit of an, I mean, the centering has to be the inverse of the centering that you get for tau k. So it's a bit annoying to write. Okay, so let me, yes, so assume that E rho 0, 2 is finite, then under E0, xn satisfies. So what we have is that xn minus E0 of xn divided by square root of n converges to z, where z is a Gaussian which has variance sigma 2 over v3, okay, where v is the speed of the simple random walk. It's 1 plus e of rho 0. 1 minus e of rho 0 divided by 1 plus e of rho 0. Okay, and yeah, so what's behind this? Well, there are two things. So first, yeah, you have that, well, the central limit theorem for tau k, well, it tells you about the variation of tau k around its mean, but tau k is directly related to x star n. Okay, so it's not surprising that if you have something about the distribution on this, you will have something about this distribution. Yeah, it turns out that yeah, if you want to make this this n like something that varies diffusively around the mean of tau k, then when you invert things, you will have this this v to the power 3 that appears. Okay, so this kind of thing gives you the central limit theorem for x star n, and actually, okay, this is true, but I think what the result you obtain directly from this computation is this. Okay, with Vn. And yeah, I don't know how different these two things are. But yeah, the difference has to be little o of square root of n. Perhaps it's much smaller than this. Okay, now how do you get the central limit theorem from xn from the one you get from xn star? Well, the idea is that xn, well, x, I mean, when you're transient, so lemma, if, so this is something I already told you, if log rho 0 has negative expectation, so if you're transient to the right, then it's difficult to go to the left. So then the maximum over m smaller than n of x star m x star, yeah, x star n minus xm is smaller than c log n for some c positive. Okay, the c depends on the distribution of rho. Okay, I'm quite convinced that this is true. Actually, in the lecture notes, it's proved with log n square. I guess it's to avoid to have a constant that depends on the distribution. So. But anyway, yeah, this is much. Yeah, this is much smaller than the fluctuations you have here. So this tells you that if this satisfies central limit theorem, this has to satisfy the central limit theorem. Okay. and I think we are done for today. Okay. Yeah, so we are going to do this by hand, and I think for this I would like to use like the potential of the walk, and this will give us a nice transition to Sinai's theorem, which is basically a limit theorem of this kind, but for the recurrent case. And I think this will this will kind of close what we have, what we want to say about random walk in random environments. Okay, and yeah, I will try to design some interesting exercises and to handle them to you by the end of the month. And the idea is to give you 15 days to give me answers, and I will do the same for the polymer part.
So next week we stay with random walks and
Yes. Then yeah, the transition will occur yeah, around this time, okay, plus or minus one lesson. Okay. Yeah, and yeah, I'll probably my second child will be born shortly after February, so you will have to wait a little bit to get the marks. Okay. Thank you.